The ledger support class manages individual ledger entry records, handling both insertion and validation of the blockchain fields. As with the ledger transaction class, it has a single constructor that accepts and stores a list of ledger entry records. These may be new records being inserted or existing records that can be validated. Ignore the Allow Update Triggers section for the moment. I'll discuss that later in the clip on securing the blockchain. Next, you see a utility function called getLock, which performs a forUpdate query on the first block, the one with a sequence number of 0, storing that block in the first entry variable. It also reports an error if it finds more than one block with a sequence number of 0, but that should never happen. Why do we perform this lock? The Apex language has poor support for multithreading, yet Salesforce itself is multi-threaded, supporting asynchronous operations. It is very possible for multiple threads to try to insert records at the same time. On a blockchain, this could be fatal. We don't have a mechanism for resolving record contention as you would find in a distributed blockchain. Apex does not have a global mutex, but a database lock will serve that purpose. We lock on the first block instead of the most recent to avoid any possible edge cases that might occur where one thread adds a new block that would then be picked up by a different thread. If more than one thread tries to insert records, one of them will get the lock and be able to proceed, while the other thread waits until it is finished. This ensures the integrity of the blockchain. There will be no duplicate sequence values. There is a very unlikely edge case that could occur if two threads try to add the first block at the same time. This could only happen once in the history of the ledger and would be detected quickly by the test for multiple first blocks, so I think this solution is more than adequate. The setErrorRecords function is used by getLock and other functions to block record insertion by using the addError method on the ledger entry sObject to notify Salesforce that the record is invalid. We always mark all of the records being inserted. There is no concept of a partial success when it comes to blockchain, at least not as we're implementing it. The calculateBlockHash function calculates the block hash field by combining the prior block hash value, the sequence number, and the transaction hash value. The sequence number is cast to a long to prevent validation errors due to varying numbers of trailing zeros after the decimal point. Remember, the prior block hash field is null only for the first block. The process block insertion method takes the ledger entry record, sequence, and prior block hash parameters, then uses the calculateBlockHash function to calculate the block hash and stores the value in their corresponding fields. As discussed earlier, this example will use the approach of adding the blockchain fields when a record is inserted. We'll use a before trigger. It's more efficient and avoids an additional DML update that in turn would invoke an update trigger. That would add complexity, as one of the techniques we'll use later to make it harder to tamper with the ledger is to raise errors during update triggers, and we'd need special code to allow our own update. Use of a before trigger is one of the reasons that we have a sequence field instead of using the auto-incrementing name field to control the sequence. The auto-incrementing name field is not yet initialized during a before trigger. In following Apex best practices to minimize code inside of triggers, the trigger creates a new instance of the ledger support class, which, as you saw earlier, takes a list of new entries as its parameter. It then invokes the process block insertions method to process the new records. Process block insertions does the heavy lifting of inserting records into the blockchain. As you would expect, it is bulk safe, designed to handle multiple records. It begins by attempting to lock the first record. The only case where you'd see a failure here is in the event of a timeout, which is highly unlikely, but I suppose could happen if you had multiple threads trying to insert very large numbers of records with large numbers of transaction fields. Next, it queries for and partially checks the validity of the previous block in the chain, the one that it will link to. I say partially checks because it doesn't validate the transaction hash. It assumes that the transaction hash is correct. This actually brings up an interesting issue. How much validation is really needed here? One could argue that it would be good to completely validate the entire chain before inserting any records, but given that the chain may be of arbitrary length and Apex has governor limits, it's very clear that performing such a validation during the trigger would be impossible. So this leaves two options. Create a more complex system that stores the request to insert a record, performs a full chain validation using batch Apex, and then adds the record when done? Or trust that the chain is valid, that the mechanisms to prevent tampering work, and that periodic full scans are sufficient from a business perspective, and thus do little or no validation of the existing chain during an insertion? Given that the first approach is much more complex, and its only advantage is that it detects problems a few hours sooner, this solution goes with the second approach, basically assuming during insertion that the existing chain is valid. Next, the records are processed in order. The transaction hash is calculated, the blockchain fields are set, and any errors detected along the way are recorded and cause the insertion to be rejected. Finally, you'll want to add your own code to publish the new entry to the world. Remember, part of this solution assumes that your organization is sharing the blockchain, excluding the actual transaction data. I'm not going to go into how best to accomplish this. There are so many ways to expose data from Salesforce. Most likely at this point, you'd make an asynchronous call, a future call, or a Qubel Apex call to perform the notification. You might send emails or create tasks. This may be an excellent use case for platform events that allow you to publish events inside and outside of Salesforce. The actual approach you choose falls into the realm of data integration and depends on your particular use case, and thus is beyond the scope of this course. Moving right along, the ledger support class can also validate blocks. The validate block hash function takes as its parameter two ledger entry classes, the one you want to validate and the prior block. It assumes that the prior block's block hash field has already been validated. It also assumes that for the current block, you have queried all of the transaction data fields as well as the fields used by the blockchain. It needs those fields in order to perform the transaction validation, which is in fact the first step in this function after verifying that the current block does indeed follow the previous one in sequence. It verifies that the current block's prior hash matches the block hash of the prior block, or that the prior block is null if this is the first block. Finally, it validates the block hash of the current block. The validate ordered block list method is used to validate the current list of ledger entry records, assuming the constructor was passed a list of records to validate in sequence order. It first gets the lock. This may not be absolutely necessary. I put it here with the idea of ensuring that no changes were made during validation. However, on a busy system with a large number of entries, this would increase the chances of a lock error during insertion when a validation is taking place, so feel free to remove that section if that becomes an issue. The function first queries for the entry prior to the first one on the list, unless of course the first one on the list is the very first block. It then enters a loop calling the validate block hash function for each pair of blocks in the list. The function returns the position of the first invalid block and -1 if no invalid blocks were found. I know this seems a bit odd. A result of -1 is often used as an error value for functions, but it makes sense here, so just keep in mind the result is the location of the error.